activation energy is the energy required or needed to break all the old bonds so that we have an activated complex. So the EA is the energy needed to break all old bonds. And then the delta H would be the difference between the energy of the products and the energy of the reactants. So that is the delta H. Delta H is less than 0. It's the energy or the enthalpy of the products minus the enthalpy of the reactants. And you can see that the reactants are at a higher energy than the products. That's why your delta H, or the heat of the reaction, will be smaller than 0. Wait a moment, making a mess here now. So that is smaller than 0. Okay, and then just the opposite for the endothermic energy profile. You start down with low energy and all the old bonds needs to be broken, and the new bonds have a higher enthalpy than the old bonds. So that will be the enthalpy of the products. This is the enthalpy of the reactants. And here you can see that the activation energy is what? All this amount of energy. That is the activation energy. Can you remember the stuff? Good. From last year. Now we need to move to this. So here we have delta H is greater than 0, or it's this HP minus HR will be greater than 0. Where's the Pelos glasses still? I wonder. Now, it is important to notice that particles will always have energy of motion. Now, I know it might confuse you, but in chemistry we also have kinetic energy. So the symbol for that is kinetic energy. The particles of any substance is forever in a state of motion. In gases, they can move freely. In liquids, they slip and slide. In solids, they vibrate. But they will never be at zero motion, unless the only place where the particles will, they say, will freeze absolutely and come to a standstill is at minus 273 degrees Celsius. That's the only place where the particles will stop moving. So that's the kinetic molecular theory of matter told us that. And what affects the kinetic energy of particles is that one of those favorite definitions. Something is the measure of the average kinetic energy of particles. Yes, we must keep this in mind as well. Temperature is the measure of the average kinetic energy of particles. That thing we must remember. Okay. So in this classroom, we have a mixture of gases. We've got some carbon dioxide, we've got quite a bit of oxygen, and we've got much more nitrogen. And I did some experiments earlier, so most probably there'll be some hydrogen in the classroom if it hasn't left yet, and as well as hydrogen sulfide. So we've got a mixture of gases in this room. Why aren't they reacting? So why would the mixture of gases in this classroom not be reacting? If you look at what we've got on the screen, why do you think will there be no chemical reaction? What is needed for a chemical reaction?
High temperature.
Okay, so if we look at this energy profile, what is needed for the reaction to start happening? Activation energy. So the energy of the particles in this classroom is less than the activation energy required to start the reaction. Okay, so our answer there is the energy of the particles in air is less than the activation energy. For the substances to react. Yes. Pardon?
What example of the activation energy? Like, okay, for example, we're doing a reaction, right? And then now we want to experiment experiment, right? Now, do we add the activation energy, or is it already there?
No, there's no, you'll have to add the activation energy. If you want the reaction to take place, you have to add activation energy. For example, this piece of wood is in the presence of enough oxygen.
Yes.
Why is it not setting alight by itself? it does not, the wood particles and the oxygen's particles does not have enough energy. So what do I have to do to start the reaction? I take something, now there's a possibility I can start rubbing this wood against something. I think the Khoisan people took a piece of skin and they took a round twig and they started doing this. The friction created heat energy that set the wood alight in the end. Now here I've got a flint in here with a gas, and just doing that ignites it, supplies enough energy. And if I do that, now I'm supplying the wood and the oxygen with enough energy to ignite. Now the wood is reacting with the oxygen in the air. Okay? So you can give it activation energy by heating it up.
Is heat the only form of activation?
Light can also cause a reaction. If you take a magnifying glass and you take the sun's light and I don't know if you children were naughty like my brothers were very naughty. They would take a magnifying glass and focus the light on the grass, and then the grass would set alight.
That sounds fun. So again, it's just heat.
So light could also be used, yes. Okay. Can I move on, because there's now an interesting graph that explains the situation. Sorry, I stopped the recording. Come in. Hello, meneer. So I want to explain the Maxwell-Boltzmann curve with your understanding that the particles, majority of the particles does not have enough energy to react. So somewhere on this graph we have the activation energy, EA, on the axis, on the x-axis. Now, some particles will have very little energy, but there will be a small number of particles with that amount of energy. So here, that's the number of particles with that amount of energy. You don't have to copy this. I just want you to follow it so that you will understand the curve. Then, some particles will have higher energy. So, they will plot a point there. Now, you can see the number of particles. There are more particles with that amount of energy. Okay? But it's still less than the activation energy. The air particles close to my skin is warmer than the air particles close to the window. You understand what I'm trying to say? So different air particles in this room will have different energy values. So some particles will have that amount of energy. Most particles will have that amount of energy. They won't react because their energy value is less than the activation energy. Now this curve, when you draw it for all the values, looks something like this. A very small amount of particles will have energy that is equal to or higher than the activation energy. So this part of the graph symbolizes the particles that have activation energy and higher. So that's here where I'm flicking the lighter. Here the particles have high enough kinetic energy so the reaction will take place. So this is a Maxwell-Boltzmann curve that tells you that the majority of the particles have energy less than the activation energy. Some particles has that value amount of energy, but a very small amount of particles will have that energy. Some particles will have that energy, but a bigger amount of particles. The most particles will have that amount of energy. These are the number of particles, but it's still less than the activation energy. As we go up, these particles, this energy, those particles, that number of particles will have that energy. Okay? This number of particles will have activation energy. So that's where the reaction starts. Okay? So most of the particles have energy less than the activation energy. It's only a small number of particles that will have energy higher than the activation energy. So you got it now.
So Mark, this is where you do after the activation energy. What is that?
These particles will react because their energy, kinetic energy, is greater than the activation energy, greater than or equal to the activation energy. The majority of the particles will not react. We made hydrogen sulfide, so the kids asked me to switch the fans on.
And now it affected us. Next door. We cursed it.
Well, bio also involves that because your system also produces some of it.
The mass system is going to produce
Shame, son. I'm glad you're still alive. Any rotting things will produce that, especially meaty things. Things high in protein, because things high in protein will be high in sulfur content.
Then what about sewage? Because it's
Yeah.
not that sewage.
That's
So
it.
what's in the sewage?
It's the hydrogen sulfide that's produced by the rotting organic waste, yes.
So now this graph is just showing that there's only a few particles made that have.
Yes, yes.